Mathematics is precise, concise, symbolic, and efficient. When we communicate mathematical ideas, we always strive to do so in the simplest form possible, whether that be reducing a fraction or writing a radical in simplified form. In this video, we'll study evaluating radicals. Definition: a radical, specifically a square root, is simplified when the radicand, remember the radicand is the number under the radical, does not contain any factors that are perfect squares. Note, to begin simplifying a radical, express the radicand, the number under the radical sign, as a product of the largest factor that is a perfect square and another factor. When we're simplifying radicals, a couple of rules will help us. The first one is called the product rule. If we have the square root of the product of two numbers, a times b, we can split up that radical over each factor in the product. That is, the square root of a times b can be written as the square root of a times the square root of b. If we have a quotient or a fraction, like the square root of a over b, you can likewise distribute that square root over the numerator and the denominator. Just be careful if you have the square root of the sum or difference of two numbers. In that case, you cannot distribute the radical. This is not equal to the square root of a plus or minus the square root of b. Make sure you see that's not equals. Be careful about that mistake. So let's apply these rules on example 1. Simplify the following radicals. Give an exact answer. What that means is do not approximate. If the radicand is not a perfect square, we want to reduce it as far as possible in radical form, but not give the decimal approximation. The first example is pretty simple. We have the square root of 36. Since 36 is a perfect square, the square root of 36 is equal to an exact value of 6. This is true because if I take that number and multiply it by itself twice, or square it, that gives me the radicand 36. Let's look at the square root of 132. So 132 is not a perfect square. So my goal is to write it as a product of some factor that's a perfect square and anything that's left. If you play with 132, you'll discover one of its factors is 4, which happens to be a perfect square. 4 times 33 gives me 132. So notice under my radical, I've got the product of two factors. So we can, by the radical or the product rule, split that radical over each factor. Then we can evaluate the square root of 4. That gives me the exact value of 2. Since 33 is not a perfect square and it doesn't have any other factor that's a perfect square, we're going to leave that under the radical. So the simplified form of the square root of 132 is 2 times the square root of 33. Let's see how our calculator handles this. If I want to evaluate the square root of 132, the best that the calculator is going to do is give me the decimal approximation. It's about 11.5. Now, I don't want to give the decimal approximation. I want to keep the exact value, but I want to check my answer. So I'm going to go ahead and type in my answer, which was 2 times the square root of 33. And notice the calculator gives the same decimal output. So again, I want to keep my answer exact as 2 square root of 33. But by comparing the decimal approximations, we know we have simplified it correctly. Let's look at the next example. We have the square root of 65. Now, the only two factors of 65 are 5 and 13. Both of which are prime. There's no factors of 65 that are perfect squares, so I cannot reduce this any further. So square root of 65, in fact, is in simplified form. Let's consider the square root of a fraction. We have the square root of 144 over 81. Remember from our quotient rule, you can distribute the radical to the numerator and the denominator. So I'm going to rewrite this, square root of 144 over the square root of 81, both of which are perfect squares. The square root of 144 is 12, and the square root of 81 is 9. We can reduce by a factor of 3 here to come up with a final answer of 4/3. Let's take a look at how the calculator handles that one. We have the square root of the fraction, 144 over 81, and it returns the answer, notice, in simplified form, 4 over 3. Next, let's consider what to do with negative radicands. So on example E, we have the square root of negative 45. Anytime we have a negative under the square root sign, it's going to generate an imaginary answer. So I'm going to rewrite square root of 45 as the product of negative 1, and let's look for a factor of 45 that's a perfect square. We could use 9 times 5. Then I'm going to split that radical up over each individual factor. We have the square root of negative 1 times the square root of 9 times the square root of 5. Now remember, square root of negative 1 is the fundamental building block for the complex number system. When we see that, we replace it with the imaginary unit I. So I'm going to rewrite that as I. Next factor, we have the square root of 9, which is 3, and square root of 5, which won't simplify. So we have it simplified, but this is generally not the order that we write numbers like this in. We're going to put the whole number to the left, the I in the middle to keep it out of the radical, and the square root of 5 there on the end. So our final result here is 3I square root of 5. This one you can also check with your calculator. Now I want to remind you, if your calculator is in real mode, if you try to evaluate the square root of negative 45, it will give you an error message telling you, oh, that's not a real number. So remember, you have to give your calculator access to the complex number system. You can do this by pressing your mode button, using your down arrow key to the real line, highlight A plus BI, the standard form of a complex number, and press enter. And then you can quit back to your home screen. Then, when we retype square root of negative 45, we get the decimal approximation 6.71, but notice there's an I on the end, so we know it's an imaginary number. Now, let's type in what we came up with. We came up with 3I, remember second decimal gives you the I, times the square root of 5, and notice the decimals match. So our simplification is correct. Okay, one more problem. We have the square root of negative 20 over 49. We'll begin with the quotient rule, distribute the radical to the numerator and the denominator. Now, we're looking in the denominator here. Square root of 49 is a perfect square, so I'm going to go ahead and get that out of the way. But we need to break down the square root of 20. So I'm going to rewrite that as negative 1 times, now I want a factor of 20 that's a perfect square. 20 can be written 2 times 10, but neither of those are perfect squares, so that's not helpful. Let's think of 20 as 4 times 5. And then we can split the radical over each individual factor and simplify from there. The square root of negative 1, as you know, is the imaginary unit I. The square root of 4 is 2. 5 is not a perfect square, so it stays under the radical. And then, writing it in a presentable form, we can call it 2I square root of 5 over 7. For good measure, let's check with our calculator. So we'll evaluate square root of the fraction, negative 20 over 49, and we'll get a decimal approximation. And then we can type in our answer, 2, remember second decimal to pick up the I, 2I square root of 5 divided by 7. And comparing the decimals match and they both have the imaginary unit. So we can be confident that we have the right answer. Just like with the fraction, you always write a fraction in reduced form. If you have a radical in your answer, it's necessary to write it in simplified form as well.